Hi, this is the video for the module 13. In this video, we're going to be talking about chi-square tests. First, some characteristics for chi-square tests. First, unlike the other tests that we have seen so far for proportion, for population proportion, and for population mean, the chi-square tests they have to do with categorical variables. They have to do with categorical variables, and we have three types of tests. The first one is the goodness of fit. The other one is for independence. Or association. And the other one is for homogeneity. So I'm going to be explaining many properties for this test, yeah, as I am explaining and doing some exercises from Achieve, some conditions that they must be satisfied, how to set up the hypothesis, what is H null, what is the test statistic. But essentially here I want you to remember we are going to be performing hypothesis tests, and the structure is going to be the same as before. What is the structure? Set up the hypothesis, H null, HA, H alternative, level of significance, test statistic, compute the p-value, and if the p-value is less than alpha, than the level of significance, reject H null. It's the same structure, but the hypothesis, the test statistic here, they're going to change, but the structure, again, is the same. So, let's say the first example. First example from Achieve, stress and heart. It says, you read a newspaper article that describes a study of whether stress management can help reduce heart attacks. The 107 subjects all had reduced blood flow to the heart, and therefore they were at risk of heart attack. They were assigned at random to one of three groups. The article goes on to say, one group took a 4-month stress management program. This is the first kind of four-month stress management program. Another underwent a 4-month exercise program. So stress management exercise. And the third received usual heart care from their personal physicians. In the next 3 years, only 3 of the 33 people in the stress management group suffered cardiac events, defined as fatal or non-fatal heart attack, or a surgical procedure such as a bypass or angioplasty. In the same period, 7 of the 34 people in the exercise group, and 12 out of 40 patients in usual care suffer such events. Use the information in the news article to make a two-way table that describes the study results. What are the success rates of the three treatments in preventing cardiac events? All right. First, success rates. In this case, they are not very complicated. It's simple because, for example, for the stress management program, it said that 3 out of 33 they suffered a heart condition or well, something like a kind of a heart attack. So 3 out of 33, but this means that 30 they didn't suffer that. So you need to divide 30 by 33. 30 divided by 33. And if you do that, is 0.90, 0.9099. So, but in percentage, you will have to write 0.9091, or in percentage, write it 9.91. Has to be in percentage because of this. Okay, so to your result, only multiply your result times 100. And the same for the exercise program. 7 of 34 they suffered, so 34 minus 7 is 27 divided by 34. That is 27 divided by 34, and this is 0.79. Or 79.41%. So use this one, all right? For the usual heart care, 12, it says 12 out of 40. So that means that 40 minus 12 didn't suffer that. So it's going to be 28 out of 40. And this is 0.7. 0.7, or in percentage, 70%. Now, find the expected cell counts under the null hypothesis that there is no difference among the treatments. So here, first, hypothesis, H null, no difference. Among the three treatments. H alternative, the opposite. There is a difference. Of course, we're trying to say that if there is a difference as to the success rate, yeah, that is the point. But there is a difference. In this time is a chi-square test of homogeneity. All right, what do you have to do first here? We need to compute the expected cell counts, or expected counts. To compute that, usually you're going to be given a table, something called a QA table, and that is related always when we are dealing with a chi-square test, but we don't have it here. You see that? So in this case, I'm going to explain how to create a table. Let me include one new page. All right, so here essentially we have two variables. The first one is stress program. And the other one is cardiac event. So in this case, this variable has two outcomes. A cardiac event occurred or it didn't occur. So I'm going to identify this as it occurred or it didn't occur. There you go. Now, as for the stress program, we have, remember, three. The first one is, let me put this below. The categories for the stress program are 4-month, management, 4-month exercise, and personal care with a physician. So notice these variables, of course, they are categorical variables. Yep. There you have. And now, and of course, this column represents stress program. This variable and this variable. And now here we have to put the counts again. Always, usually when you are dealing with a chi-square problem, you will have to end up with a table like this. In this case, it's not provided, but anyway, we have to compute it. But how? It's simple. For example, for the 4 months management, how many cardiac events occurred? 4-month stress, 3 out of 33, but don't put out of 33, only put 3. So 3. How many did not occur? 30. Yeah, in this case, because we have only 2 outcomes for this variable, but even when in this case we have 2 outcomes for this categorical variable, sometimes we can have even more. And the same for the other ones. For this one, it's going to be 7. If I'm not wrong, 7. Out of 27, did not occur 27 because the sum in this way, here we have 33, here we have 34, and this is 12. 12. And the complement is 28. And this is out of 40. You see the total. And here is convenient that you compute the total as well here. This is 3 times plus 7 is 10 plus 12 is 22. And this 30 plus 27 plus 28, I think is 85. The total. Of course, in the two ways, the grand total should be the total number of, in the sample. In this case, it was 107. See that? If you add this in the two ways, this is 107. 33 plus 34 plus 40 is, this is 67 plus 40 is 1 out of 7, right? So it's 1 out of 7. So again, usually you're going to end up with a table like this. Now, when you are performing a test, what kind of test we are performing here? Homogeneity, this one. Yeah, I'm sorry if I'm not pronouncing this correctly, but this homogeneity. Yeah. So this, when you are performing this test, you need to compute something that is called the expected cell counts. How do we compute this one? You are going to need this table. Now, after this, I will explain how to do this. I mean, we can do all of this in Minitab, right? But first, I wanted to know how to do it. I mean, how to compute this by hand, because for this exercise, you will have to do it. Well, actually, I can right now put everything in Minitab, but again, I will explain how to compute it, and then we're going to verify our answers in Minitab. So here, for example, for one. First, I'm going to compute the expected cell count for this one. Notice, this cell corresponds to 2 outcomes for each variable. For example, this one is 3 is what? 4 months management, and it occurred, a cardiac event. So in this case, I'm going to put it here, expected count 4 months, and it occurred. How do we compute this? You are going to multiply the total in the row for this one for 4 months. The total is 33 times the total for the column. I mean, the column where this is it occurred 22. And divide by the grand total, 107. So I repeat. For this one, for example, we want to compute the expected counts. Go to the total in the row, 33. Go to the total in the corresponding column. This had the row for months and the column it occurred. 33 total of the row times total of the column divided by the grand total. And if you do this, you are supposed to get 6.79. Verify that if you want, please. And that is supposed to be the answer here. 6.79. and so on for the other cases. So on for the other cases. For example, if you want to compute the expected count for this one, uh, for 4 months, but it didn't occur, you will have to multiply what? The row, 33 times, but now we are in this column, 85, and divided by what? By 107, and so on. So you will have to pay attention to where each number is according to the row and the column. Multiply the total row, total column, and divide by the grand total. This is how you're going to compute the expected count if you are going to do this by hand. Okay? But fortunately, we don't have to do it by hand. We have, all of this because we have Minitab. So how to do this in Minitab? I will explain how to do it. All right. To compute this in Minitab, you have to go to Minitab. Here I have Minitab. Notice, once you have created this column, or if this table, or if this table is given, in this case I created the table, but you will see in some exercises that this table or this kind of table is given. So in this case, you will have to enter only the numbers from the table. That's all. Where in some columns, for example here, I'm going to enter the numbers for this column, 3, 7, 12. 3, continue without autosave, 7, 12. And then in the other column, 30, 27, 28. Yeah, if you're saying, I don't have to put like a name or something, no, you don't need to do that. We don't need it, right? I mean, if you have the table and you know the meaning for each cell, you don't have to do it in Minitab. Only enter the values, 30, 27, 28. 30, 27, 28. And there you have it. Now, once you have this, and notice I put this in column 1 and column 2, you will have to go to Stat, Tables. In this case, chi-square test for association. Yeah, I know we're computing this for homogeneity, but it's essentially the same. I mean, the same computations. And choose the option summarize data in a two-way table. And there you have. And then columns containing the table, this one and this one, C1, C2. Here you want to put in a name for the rows and the columns, you can do it, but again, you don't have to do this, all right? And then what else? I think everything is okay. We want the expected cell counts. Okay, and then okay. And after you have done this, notice, you will have these are the values, 330, and below you will have the expected counts. For example, for the number 3 is 6.78, should be the same what we got here, right? Well, it's 6.79, it's rounded up. So for 30, 26.215, for 7, 6.991, so and so on. So now you know how to compute this by hand, or you can do it in Minitab. But again, if you are going to do it in Minitab, and of course you can do it right in this class, you need to have this table first, okay? In many problems, this table is going to be provided, but if not, you will have to construct it in the way as I did it. So now you have all of this below for each number are the expected counts. So let me put them here. $6.79 for this one exercise program and cardiac event occurred. 6.99. For personal or usual, 8.22. Discontinues here. Stretch management and it no cardiac or it didn't occur. It's 26.21. For this one, 27.01. Exercise and no, it didn't occur. And personal or usual and didn't occur, 31.78. There you have. Again, how did I get these values? From the results of Minitab. For example, usual, well, I call this personal, or the number personal care, and it no cardiac or it didn't occur is 28. The value is 28. The value is 28, but the expected count is 31.78. And it's the value we have here. See that? This one. And so on. Okay? Now, next question. Do the expected counts meet our guideline for use of the chi-square test? The answer is yes. But what is that guideline? All the values for the expected counts should be, or must be, not should, but must be greater or equal than 5. Must be greater or equal than 5. That is an assumption, right? Well, I mean, something that if you want to perform this test, this is one condition that it must be true. Must be greater or equal than 5. But in this case, notice that for each cell, all the expected counts, we have more than 5. So no problem in this case. So that's what I put yes. Next, is there a significant difference among the success rate for the three treatments? Compute the chi-square statistics. Use table D to approximate the p-value of the test. How do we compute this? All right. Now, again, go back to Minitab. We have these values here. Go to Stat, Tables, chi-square test for association again, statistics, oh, I'm sorry, I already did it, right? I'm sorry, I was about to click this box, this one here, chi-square test, but I already did it, right? I'm sorry, I didn't pay attention before, but yeah, if you didn't do it, you have to click this box. Repeat the process and click this box, chi-square test, and then OK. Oh well, I can put cancel, right? Because I already did it, so it should be here. Yeah, it's here. Notice. Yeah, I'm sorry. So we already have the chi-square test. We have to pay attention to this chi-square Pearson. Ignore this one, likelihood ratio. We don't talk about that here in this class. So the one for which you have to pay attention is this one, Pearson chi-squared. The value is 4.84, and the p-value is 0.089. So let's see on the homework, you're going to have several options, but notice 4.84, all of them, they have 4.84, but the one that is, I think this one, right? Less than 0.01 and 0.1 and greater than 0.05, because the test is 0.89. So yeah, I think that is the answer. There you have. Now, the level of now we have the p-value that is 0.08, and again, How do we know that whether we have to reject the null hypothesis or not? Again, this is true for any hypothesis test. If the p-value is less than alpha, in this case, I don't know why I think this exercise they don't say at the beginning what is the value for alpha, but again, if they don't say, use alpha equal to 0.05. So if the p-value is less than alpha, we have reject H null. So do we have to reject in this case? The p-value is 0.08. It's not less than alpha, right? It is not less. So we don't reject. Since p-value that in our case is 0.089, is not less than alpha equal to 0.05, we don't reject H null. We don't reject H null. So if we are not rejecting what? This hypothesis. If we are not rejecting this one, then the evidence goes in favor of this one, right? I mean, to say that no difference between the three treatments. So I think the option, now, of course, you don't have to write it here. You will have to select from the option from achieve. So I think the one is, there is not enough evidence to conclude that the success rates for the various treatments are different. So this one. Yeah, because they seem to be the same. Yeah, I know. In the problem, of course, the rates, this one is greater, 90%, 79, and 70%. But anyway, even with that, it seems that there is not a significant difference. So that's why we don't reject H null. All right. Next example. It says, this is different ethnicities. Individuals of different ethnicities are somewhat more genetically variable than those of the same ethnicity and may respond to treatments differently. The FDA has recently requested that every effort be made to include individuals of all major ethnic backgrounds when enrolling subjects in clinical trials. A randomly chosen article in the New England Journal of Medicine describes the efficacy of calcium and vitamin D supplementation in preventing hip and other fractures in healthy postmenopausal women. The table contains the breakdown by major ethnic group of the subjects whose ethnicity is known, along with the percent of individuals from each ethnicity in the general American population. And there you have. In this case, notice we have the counts for the study, the counts on the values that are supposed to be true, the percentage, all right? The counts in the study, they were 153, 3,000 for white, 30,000 for black, 3,000, 317, Hispanic, and so on, right? Native American. And these are supposed to be the true values. So this, at the beginning, this might be confusing, right? Because here we're having this suppose that the ones that are supposed to be the true percentages, right? But we don't have the percentages here. We have from the study, we have only the counts, so we need to compute something here. All right. First, what are the hypotheses? Oh, by the way, notice in this example, and this is from Achieve, it says to access the complete data set, click the link for your preferred software format. You can do it, but you don't have to do it, right? Because we already have here this table from the result. This table is not for me, right? It's actually This is from the problem. So if you see the observed for each category, be careful because they are ordered in a different way as here. Here we start with white, but the white here the last one, 30,153 is the observed, and the expected is 27,101. Yeah. How did they compute this one? Well, the true value in this case, for example, expected count for y. The true value is supposed to be 75.6, or with a percentage 0.756 times the total. The total in the sample is this one. Is this value of n, you see it? This one here. 35,848. So if you multiply this, 35,848, you are supposed to get the expected count. I got 27,101. And yeah, it's this one. And so on with the other expected counts. Anyway, again, this table with the outcomes, with the results, is provided in the exercise. That okay? I didn't put it. It is provided in the exercise from Achieve. And you already have this here. And this case, we're trying to perform an hypothesis test. Hypothesis test of goodness of fit. We want to see whether the observed, or what we saw in the sample, is equal to the true, between quotation marks, to the true distribution, right? The distribution is supposed to be this one for each ethnicity, but the evidence, maybe they say something different. So the hypothesis we have to set up here in this case, notice we have probably proportion for Asians, Black, Native American, white for each of these categories, Hispanics, yeah. All of them here, you have to choose always that each of these are equal to something. Versus the alternative is that they are different. So be careful with this one, because all of them, they have the null hypothesis, the proportions for each equal. But the only one that is true, I mean, that is the opposite, is not this one, because this is less but could be greater. I think this one, that this one is not true. Just be careful that you have the right numbers. I mean, so the one that has this PA is Asians, 0.038. Yeah, 0.038. Black, 0.108. Yeah. Hispanic, 0.091. Hispanic, 0.091. Native American, 0.07, 0.007, and white, 0.756. So yeah, this has the true values for each category, and but it doesn't have all of them different, or that is not true. So I think the one that is correct, the option that is correct is the one with these numbers in the null hypothesis, but the one that says not true. So I think it's this one, right? Yeah, this one. Be careful because there is another one with the alternative, not H null, not true. But notice this one here for the Native American has 0.004, but that is not the true proportion. The proportion is this one, 0.7 divided by 100, 0.007. So be careful with that because this is kind of tricky, right? Are the conditions for the chi-square satisfied? Remember, all of this, all of the expected should be greater or equal than 5. And yes, they are, right? So in this case, yeah, it's true. So you put yes. So we can perform the test. Select the option with the chi-square statistics and p-value for the test as reported by the provided Minitab output. Again, this was provided already in the example. The chi-square is this one here. 1,709.77. So it has to be either this option or this option. Now you have to be careful as to what the p-value is. The p-value is, notice, it's almost 0. So it's less than 0.001, so the right option is this one. So the p-value is, again, use alpha equal to 0.05. Do we reject the null hypothesis? Yes. Why? Since the p-value that is 0.000 is less than alpha 0.05, we reject H null. Again, that I'm sorry if I repeat this many times, but I think it's important that you keep this in your mind. If the p-value is less than alpha, reject H null. Always, for all the hypothesis tests we see in this course. So we are rejecting what? That we are rejecting this one. That the distributions or the proportion for each is according to this. So this is not true. So we have evidence to say that this distribution is not true. So next, you have to pick the right option. I think this one is, there is strong evidence that the ethnic distribution of a study participant does not match that of the American population. Yeah. Does not match this one. Because we are rejecting H null. All right. Next example. Inbreeding dogs. A field biologist recorded events of inbreeding in a colony of prairie dogs based on a sample of 44. I'm going to highlight important information. 44 Strauss females and 17 sexually mature males. The researcher computed the coefficient of relatedness, I don't know what it is exactly, of following possible male-female pairs in this sample. If individuals avoided inbreeding, we would expect to observe breeding mostly between individuals with little genetic relatedness. On the other hand, if breeding occurred randomly, without regard for the genetic relatedness of the mating couple, we would expect breeding observations among individuals of various relatedness to be proportional to the number of possible pairs with a given coefficient of relatedness. The table contains the observed and expected breeding pairs in this study. So in this case, we're lucky because we already have the observed and the expected pairs. Is that okay? And it says to access the complete data set, click the link for your preferred software format. But I think you don't have to do it either if you don't want. I mean, you want to do it and you want to manipulate this more, no problem. But notice, we already have the test statistic, right? We already have the test statistic. So let's see what this is asking for. First, set up the null hypothesis. Plan, test, H null. So it's already given, you see? The population proportions match the expected proportion based on random combinatorials versus H null. So in this case, what kind of test is? Is a goodness of fit test. Because we want to test whether the population proportions match the expected proportions, right? So H null is false. Are the conditions for a chi-square test satisfied? Essentially, the only condition you have to verify is that what? These values are greater or equal than 5, but it is true, right? So yes, the answer is yes. This one. What is the p-value given by the table or the software you use? All right, the p-value is computed with this, the probability that the chi-square distribution is greater than the value of the test statistic. In this case, the test statistic is 9.377. So 9.377, we need to compute this. How do we compute this? We have to use Minitab. So go to Minitab. You will have to use the, I think it's calc, probability distributions. We have the value, we want the cumulative. So you should this one, cumulative. Should the distribution choose chi-square? Chi-square, there you have. Degrees of freedom. What are the degrees of freedom? In this case, for goodness of fit, degrees of freedom are going to be equal to the number of categories. In this case, 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1. So in this case, it's 7. So the degrees of freedom in this case is equal to 7. So with that, that is the value we have to specify here. 7. And the value is what? Is 9.377. 9.377. And I think that's all what we need by now. So, okay. And notice, you are going to be given this, but this is the probability that the distribution is less or equal than the number. But we don't want that. We want greater. So in this case, it's going to be 1 minus the probability that the chi-square is less or equal than 9.377. And this probability is provided in the table, 0.7733. 0.7733. And this is equal .2267. 0.2267. That is the p-value. So choose the right option. This is the p-value. I think our p-value is between 0.20 and 0.25, right? So this is the option. This one. There you have. So, do we reject H null or not? The p-value is 0.22. Again, it doesn't say, but you have, if it doesn't say, use alpha equal to 0.05. Do we reject H null or not? No, right? Because the p-value is not less than alpha. So we don't reject H null. We are not rejecting this. We are not rejecting that the population proportion match the expected proportion based on random combinatorials. So we are not rejecting this. So we can say that this is the evidence goes in favor of this, that the population proportion matched the expected proportions, right? So what is the right option to choose? I think I'm sorry. Yeah, I'm sorry. We're talking about inbreeding dogs, right? Yeah, I'm sorry. So I think the one should be there is weak evidence. No, there is strong evidence. Oh, yeah, I know this can be tricky, right? As to what is the it's better we can write down our own conclusion, but here we have to choose the correct one. I think the one there is not enough evidence to conclude that breeding among prairie dogs is not random regardless of genetic relatedness. Yeah, so that the distribution is the same. So I think it's this one. The data are consistent with the researcher's hypothesis, so that the expected pairs is this one. I mean, the expected pairs or the distribution is supposed to be correct. That is what we are saying here. Yeah, I know. I know. If some of you think that sometimes when you have to apply this or write down the conclusion, you need to know some aspects of the technical or technical concepts from the problem. Well, that depends, right? I don't think so, right? I mean, I know how to apply this, but I don't know many of the context or the technical concept that for these problems. I mean, I understand how to apply the statistical methods, but that doesn't mean that I can understand everything where they are applied to. Yeah. All right. So one more example. Carcinogenicity. I'm sorry, I don't know how to pronounce that word, but I think it has to do with cancer. I don't know if I wrote it correctly. Anyway, yeah, I'm sorry for that. So, but it says the U.S. National Toxicology Program (NTP) studied the toxicity and carcinogenicity of agents potentially causing a risk to human health. Electromagnetic fields around electrical installations are harmless in theory, but they might have a long-term effect on health, for instance, in triggering tumors. Observational studies in human populations have suggested a potential association. So here, if you see this work, it's very likely that it's going to be a chi-square test of independence or association because of this work, this one. So I wanted to know something. I know I didn't explain many details, but when you are performing this test for independence or the one that we saw at the beginning, homogeneity, the computations are essentially the same. The only time when it changes is when we have to do a chi-squared goodness of fit. But well, an NTP study looked at the occurrence of cancers in otherwise healthy rats after 2 years of daily exposure to 60 Hertz electromagnetic fields of various intensities. The numbers of male and female rats with a tumor after the 2-year study period is displayed. Note that 2 Gauss is approximately 1,000-fold greater than what is considered high exposure for humans. And there you have this table. Question, is there significant evidence of a relationship between tumor rate and electromagnetic exposure in male rats? All right, here you will have to create the table. So how? You will have to create one table for male and other one for female. So let me create it here. I'm going to create the one for male, and you will have to do the one for female. So male. The categories for the kind of exposure is control, no exposure. No exposure. .02 Gauss exposure. 2 Gauss exposure. And notice the ones they have a tumor, they were, for example, for the control, no exposure was 16. So here I'm going to add the options tumor, no tumor. So the tumor is, we have, notice, for males, we have 16. 16 out of 99. So how many they didn't have a tumor? 99 minus 16, that is 83. And the same for the other ones. Again, this is only for male. You will have to create another table for female. Is that okay? Male rats, 0.02 Gauss exposure is 31 with tumor. 31, no tumor. 100 minus 31, 69. 2 Gauss exposure is 30 with tumor. No tumor, 100 minus 30, 70. And there you have your table. Remember this two-way table. So now what do you think you have to do? Of course, we have to put this into Minitab. So again, I'm going to put only the columns 16, 31, 30. I'm going to do it, since I have used the column 1 and 2, I'm going to put it in the columns 2, 3, and 4. 16, 31, 30. 16, 31, 30. 83, 69, 70. There you have. Again, I'm doing this only for male. You will have to do this for female. That okay? So once you have this, perform the, you can compute the expected counts and the chi-square test. How? Stat tables, chi-square test for association, summarize data in a two-way table. Columns now, they are in C3, C4. If you want to put the name for the rows, so that is up to you. You don't have to do it. Statistic, be sure that you have the option for the chi-square test and expected cell counts. Okay, okay. And there you have. There you have the expected counts. Expected counts, remember they are below for each. But in this case, I don't know exactly what this is asking. I mean, this problem. So, oh, the first question is, do the expected counts under the null hypothesis satisfy the condition for using a chi-square test? Remember, we need to have what? We need to have each expected count greater or equal than 5. So yes, it is true, right? So yes. Yes. This is for male. Use the software of your choice or table D to give the statistic, degrees of freedom, and p-value. So in this case, we have only the degrees of freedom here are, notice, when we are performing this test, chi-square test of independence, the degrees of freedom are computed in a different way, as in the case for the goodness of fit. In this case, the degrees of freedom, I'm going to explain here, they are computed by number of rows minus 1 times number of columns minus 1. So in this case, we have 3 rows, so 3 minus 1 times columns 2 minus 1. So it's going to be 2 times 1 only. So the answer is 2. You compute the degrees of freedom when you have independent, when you are testing independence or homogeneity. So don't forget that. So in this case, the degrees of freedom is 2, but the chi-square, we already have it. Go to Minitab. Oh, by the way, notice you don't have to struggle, right, with the degrees of freedom because it's already given there. So the chi-square test, remember the one person, ignore the other one, 7.146 and degrees of freedom 2. So what is the right option we have to choose? Is this one. Oh, we also need the p-value, right? The p-value is 0.028. So what are the one with all the options? Is 7.146, degrees of freedom 2, and p less than 0.05, greater than 0.025. This one. Yeah, because the p-value is 0.028. So what is the conclusion? Again, this is done. We don't have the null hypothesis, right? They don't have it here. But well, anyway, H null, since we have independence or association, there is an association, potential association between exposure and tumors. There is No, I'm sorry. In H null, you have to put independent. The variable exposure and tumor are independent. Always, this is the null hypothesis when we talk about a test for association or independence. H null, H alternative, the opposite, exposure and tumor. Oh, we're talking about male rats. Male rats are dependent. We are talking about male rats. Do we have to do it for female? So again, use alpha equal to 0.05. It doesn't say otherwise. So do we reject the null hypothesis? The p-value is 0.02. So yes, remember the p-value was 0.028. So yeah, we have to reject the null hypothesis. So we reject this one, that they are independent. So there, it seems to be there is an association, right? Because they are dependent. So the right option here is, I think, again, yeah. What are the one here? There's no evidence of a difference in tumor rate. There is good evidence of a difference in tumor rates among the male rats. I think it's the second one. I think it's this one. There is good evidence of a difference in tumor rates among male rats depending on electromagnetic exposure. So yeah, there is some kind of association, right? Because we are rejecting this one, so we are kind of accepting this one. So they're dependent. So I think the one is this one. And is there significant evidence of a relationship between tumor rate and electromagnetic exposure? Yes. Yes, in male. No, this is for. No, this is for. I'm sorry. I thought this was for the other one, but this is for the female. We're working with the male. Oh, there now. This is part B. This is for the female. So we are done up to this part with male. Now you have to complete this one. You verify this one. Anyway, I will give you the answers. You will have to create the table like this one, right? But now for female, I created this for male. Now you create the one for female, and respond to the questions. Anyway, the answers are this: yes. The chi-square is going to be 0.362. Degrees of freedom is going to be this one. Please verify that by creating the table. And the conclusion that can be made is there's no of a difference. It's going to be this one. But please verify this, okay? And here you will have final this question in part C, which summarizes these findings. Sort the answer options and as they correspond to either yes or no. Well, here I don't have the options, but do we have to select this from an answer bank? But here we have to choose male and female rats appear to have similar, and this continues. But with this, you can identify it. The other one is males, but not females. Appear to be sensitive to electromagnetic, and then with this you can identify and continues, all right? And for no, male and female rats appear to have similar, and it continues. Other one, females appear to be more sensitive, and it continues. And the other one, males develop more tumors than females. And it continues. So I think with this you can identify how to choose the answers, right? Please complete the table for female. You have the answers here, but anyway, verify the answers. All right, that's all by now. See you in the next video.